for Professor Michael Mahoney's invitation. And this is the picture I took for the computer science UIUC called Thomas Sieber Center. So it looks quite gigantic, a big building, hosts all the faculty and students in computer science. So my talk is on metapath-based approach for similarity search and mining of heterogeneous information networks. The work I've done in computer science together with lots of students, especially I should mention Yizhou, San, Mingqi, Chi Wang, Bo Zhao, and Tim Weininger. These several people contribute most to the technical contents of this talk. Okay. So of course I should acknowledge the support from many different sources, you can see. So the discussion we got in, like last year, actually Professor Michael Mahoney came to UIC to both Department of Statistics and Department of Computer Science to give talks. When we got into this, I was discussing about the metapaths. He got a lot of interest on this. Then we will see why this is particularly interesting on data mining, especially mining heterogeneous information networks. I think everybody knows the network, especially people working on social networks, work on the web, biological networks, or research collaboration, product recommendation, many things can be think they are networks. Okay. But many people treat these networks as homogeneous networks. What means homogeneous? They can think those are single-typed, single kinds of links. For example, think of social networks, people are thinking, friends link with friends. Or you think about a web, you think web pages link with web pages. So these we call the single-type, single-linked, networks. Those are we call homogeneous networks. But in real life, many networks actually are linked through multiple typed objects. Just give you a simple example. This actually is the author, one of the students of mine, Yizhou San. You can see these are the papers, these are the conferences, these are the authors. Actually, the link, even we say we got a co-authors. Actually, the co-author is linked with, via some papers or conferences finally get together. Okay. It carries lots of interesting information. For example, if you just look at a movie network, if you say, oh, those are just co-starring, this movie, so these are the co-stars. It doesn't make too much sense. But if you say which movie they got together, okay, become the actors and actresses together, and who are the actors or directors, probably will make more sense. So if you even look at Facebook, if you think of a Facebook, you're linked for what? Okay, that probably also make a lot of sense. So to that extent, if you think you model everything just to get rid of multiple typed information, just thinking people linking with people, you got a homogeneous network. Actually, you can think it's an information loss projection of the heterogeneous ones. So we think the heterogeneous one carries more information. If you want to do data mining, you should not lose it. Okay. So just give you an example. If you think about healthcare, okay, the doctors, patients, they are all people. But they are different kinds of people when you do the medical. One is a patient, the other one is doctor, plus disease treatments. They link together. They form heterogeneous networks. Then you think about even software. There are projects, developers, programming languages, project different categories and codes and all things. So they link together in different ways. The same thing as, for example, even you look at news. We have the writers, we have person, we have organization. Different locations, different events, they link together. So I just take one running example, which is we call DBLP, which is Computer Science Bibliographic Database. Okay. You look at this. This is the first one, just one entry. This is the one we published in Wisdom, this 2012. So you can see these are several authors, okay, co-authors. But they make sense only you can see what they are co-authoring. It's papers, okay, and where they publish. So what we say is we got a database. The database contains about 2 million papers, about 500,000 authors, and different papers they link together via different conferences. What we can get from this kind of database? People say, I will know which people write which paper when they evaluate for tenure. I can just check the database. Okay, that's just one use. Now I just list a bunch of uses. You probably see it's quite interesting. The first thing is how computer science research is structured. How many fields, subfields, and nested subfields. How they evolve. Okay, who are the leading authors on particular issue, like information retrieval, or what are most popular terms or authors or venues in each field or subfield. And for example, Yuri, I don't know whether he's here. He's going to give a talk, Yuri Leskovic from Stanford. Who are the peer researchers, most similar ones, okay? And whom Chris's Falusa is going to collaborate with, what kind of topic they are going to work on. And there are many, many things you think it's almost impossible to get. Actually, it's not too hard to get once we view them as a typed heterogeneous information network. So my talk on this is exploring the similarity, exploring the data mining part. I'm going to give you, if you look at this, the first thing is I want to explore the rich semantics of heterogeneous information network using 2 algorithms. One we call rank clustering, another is rank classification. I'll give you these 2 algorithms. You see, it's quite interesting to study it. Then I'm going to introduce you more systematic methodology we call metapaths. Okay. Then we study metapath similarity, prediction, including path selection. I'll give you some open problems, the grand challenge, how to construct this network. Okay, let's first start with the first algorithm work out in 2009, published in EDBT in St. Petersburg, Russia. It's a European database technology conference, okay, called RankClus, rank and clustering. Okay. The general philosophy is, if you want to describe large number of things, very important thing you want to group things together, because if you get it like 500,000 authors, it doesn't make sense to enumerate them. But if you cluster them into different fields, it makes a lot of sense. Another thing is ranking. Everybody knows page ranking. Then you know the ranking is so important. Otherwise, you type a keyword or name. If you got 30,000 entries found, there's no hope you even want to look at it. Okay. But once it's ranked, the most important thing is on the very top. That immediately makes a lot of sense, right? So, but a few people are thinking putting ranking and clustering together, actually they really help each other. Why? Okay. So I think here everybody knows clustering. And most people are thinking about clustering is every object you want to cluster, actually they sort of equally important. Okay. Then you will say, oh, these several guys in one cluster, this in another cluster. But in reality, it is not. For example, okay, you just think about, suppose we got, like a person, suppose Mike, okay, is in this field, in the statistics, data analysis one. But we may get one PhD student in Stanford, just first year as it came, okay? So if you say this student said, I'm going to change the field, I'm going to work on another thing, okay? Is the Earth going to quake? No, there's nothing happen, okay? You can change it 3 times a day, doesn't matter. But if we got a big guru, okay, say, I'm going to change, I'm not going to do this, I'm going to do bioinformatics or, robotics. Many things may change, right? His students may change or may want to quit, or there are many things, right? So you probably can see not every object is exactly equal. So why, when we do clustering, we have the thinking everything is equal, okay? So here is we say, if things are better ranked, highly ranked, we treat them more important in clustering. We probably get a better cluster. Think about this. So just thinking in this way, we are exploring the heterogeneous network. That means the simplest one. You got authors here linking with conferences or venue. Okay. If you think, actually the research are organized with multiple venues, multiple authors. Okay. You put their links, they publish in which author published in which conference, you link them together. Now we are thinking about, for each cluster, like statistical analysis or data mining or machine learning or robotics, okay, each of them, we think they form one cluster. Okay. Then we may want to say, doing some initial ranking, based on this ranking, doing some clustering, and come back to reshape my network some way. Then I'm doing ranking again, clustering again. If we do this, even every round, we improve a tiny little. Okay. Eventually, we may improve a lot. Okay. That's what PageRank was doing, right? So with this idea, we work out a very simple but natural algorithm. Initially, okay, we probably say everybody is equal ranked, okay, random cluster, okay, K clusters. Now we probably kick in some ranking rules. Say you should be ranked higher in some clusters by certain rules. Okay. With this, once we kick in, we can re-evaluate your space. You probably more important in this cluster rather than the other one. Okay. If we do this, we adjust the cluster. We do this step 1 through 3 again. Every time we improve a little, finally you can see it improves a lot. Of course, in network, everything's matrix. But the difference is, once you see this, if you got a different kinds of things, for example, you say conferences is type X, authors type Y, your matrix actually partitioned into several sub-matrices. You think this? This XX means conference linked with conference. Initially, is nothing linked. It's empty. But author, conference may link with author. Author may link with author via co-authors. So this matrix, some part is empty, sometimes it's not. Okay. But while you start kicking in the ranking rules and the classification ones, things will change. Okay. Of course, how can we do ranking? The very simple one is, for example, in conferences or authors, you can say, people publish more papers, probably rank high. Or conference take more paper, may rank high. Okay, that's one we call simple ranking. But you immediately may jump up. You say, no. The game is not playing that way. Okay. The key actually is there are some highly ranked authors or highly reputed conferences. Okay. So they do play roles in shaping up different fields. Okay. Of course, in that sense, we can refine the rule. We call it ranking-based rule, or authority-based rule. Authority ranking means, for example, if you say the very important one, you look at the second one, is highly ranked conference may attract many papers from many different authors. You think about this. Okay. Suppose your conference, your paper got rejected by certain conferences. If those are bogus or some low-quality authors, may say, we set up our own conference or workshop. Every paper will be accepted. Okay. And you think you will be ranked higher? No way. Okay. The reason is other people were not going to join you. Okay. You got those bogus paper. The people will try to shun from you. You say, no, I'm not going to send paper to this conference. So obviously, that's a ranking rule. You get a 1, 2, 3. The 3 means even co-author may play some roles. Of course, you can use slide bar to adjust how important co-authorship could be. So if you code this in matrix form, you can easily say there are authors and conferences. Okay, turn this into this kind of matrix computation. You can get a ranking of the authors and ranking of the conferences. Okay. And these actually is influenced by the collaborations. Okay. So we did this experiments just on DBLP data. It immediately looks very interesting in the sense, you look at this. Okay. We took two fields. One is database and data mining. The other one is computer architecture and hardware. We assume they do not have that many overlaps. Okay. So then you can see at the very beginning when you do random partitioning, both clustering and ranking actually is mixed up. But after a few iterations, you probably can see by grouping and ranking and then clustering again, immediately they make it very clear. Just a few iterations. These two fields, both clustering and ranking, are highly separated. Okay. So, and we can even just say, suppose we say we want to get all DBLP into 15 fields. Okay. You probably can see, we say K is 15, then immediately you can see these conferences or journals or these venues immediately becomes more separated. Okay. And they are reasonably ranked. It's not like best ranked, but still what you can see is those top ranked ones are somehow at the top. Okay. So this, remember, there's no citation information. It's just based on the links. Okay. With the links, you do the ranking and clustering. Just a few iterations, you can get this. And plus, this algorithm is very efficient. The reason is what you do essentially is kind of EM algorithm. Every time you evaluate against the center. Okay. So the center is a very small number, like 15. So it essentially is, to proportion to the number of centers. Okay. Of course, if you want to explore more refined one, you have to explore more complex networks. Okay. For example, what I showed you before was just using these two, venue and author as, bipartite network, which actually is not that good. Then you look at this. This one is you introduce term into this paper, link with term, with author, with venue. We call this one is a star network type schema. Okay. From this star schema network, once you do partitioning and ranking and clustering, you actually can see, even you get like database hardware theory. Once you get into each cluster, the DNA structure, the type structure is the same. Okay. You still have a paper linked with author, venue, and terms. But you can, doing clustering and ranking in a nice way, you can cluster them into different clusters and you can rank them based on the importance. I just show you one such cluster using this one. See, this is a term cluster. You probably can see, immediately you can see what I'm doing clustering. Because you look at this terms of database, system, query, management, object, relational, distributed processing. These are database system cluster. Okay. Then you look at these are the database conferences. These are the database authors. So you probably can see there are many, Berkeley and Stanford authors here as well. And even you can do subclustering. For example, within this database, you do another K, you do another subcluster. Here actually shows this cluster is XML X-query cluster. Then these are the top authors. Remember, there's no citation information. What you got is just the links. Based on the links and clustering, you can get quite reasonable ranking as well. And very interestingly, people actually in our university, in some other groups, they tried even on the pictures. The pictures, you get a different grayscale, different colors. You do this clustering and ranking. You can see those are the thousands of Kodak pictures. Immediately, the picture becomes different clusters. This bigger one means the most representative, the highly ranked picture. In the sense, those are most typical pictures in this cluster. So you can automatically do clustering ranking just on pictures. Yeah. Moreover, there's one researcher from University of Queensland in Australia. He actually tried on DBLP. He just say he tried on PubMed. He just wanted to know for which disease, what are the most highly ranked methods or treatments. Okay. He has no medical background, but what he used just using PubMed, he assumed people, if this treatment is going to be effective, it will be discussed in PubMed, in medical, literature, in highly regarded journals, more. Okay. Then this is HIV/AIDS. He listed 10. He listed about 20 different diseases. Get the top 10 treatments, and went back to doctors. The medical school professor in Queensland was very impressed because he said, I know nothing about medical science. I just doing clustering and ranking, and finally get top 10 treatments. It's almost at the expert level, okay? Just because the people discuss more, publish more frequently, more popularly. So you can see this exploring the heterogeneity of the typed information in network actually is quite powerful. But one fundamental issue is how can we doing the nice similarity measure, because that's a foundational one, okay? I'm going to give you a little on that one, but here I'm going to just showing you if I add a little training, okay, how things may change, because the previous one had no training at all. If we got a training, get some labor data, they're going to, using this heterogeneous network, they're going to propagate down to those unlabored part. So it becomes quite interesting. We use a graph regularization. I'm not going to give you the detail on the formulas, but it's interesting. You can see the final result with examples. Okay, we took RankClus, which is no training, very minimal one. You know, there's no training, no available class labels. But we add a little training. Okay, then we did this. We work out one called GNetMine, graph regularization based on network mining. Then in the KDD 2011, we work on another very interesting one using the similar philosophy as rank clustering. We do rank and classification. General philosophy is, even for classification, you will not think every object is equal. You will think those highly ranked objects weights more in your classification. That means those people publish more right in the center of the field, probably it's more important when you do the classification. Then you will see the result. Okay. So we comparing, you know, we took these 4 fields. Of course, we are not doing any clustering or classification beforehand, but we do give a little training. You will see how many training examples we need. And we use 14,000 papers and 14,000 authors, all in these 4 fields: database, data mining, AI, and information retrieval. Then you will see we use those types: paper link with conference, paper link with author, paper link with term, those schema. Then we compare competing with a lot of, you know, for example, those are the typical homogeneous version of the network learning, or using the, you know, the classifier using the relational classifier or several other methods. What you can see, the result is very interesting. Okay, the first interesting thing is we work out 2 algorithms. One called GNetMine, another is RankClus. Okay, GNetMine is just based on graph regularization on the network, heterogeneous network mining. The other one using ranking and classification iterative together. You will see, what do you mean this 0.1% of the training? Okay, you actually can see what we use. One is author, one is paper. That means we train something on the authors, give labor on some authors, and give labor on some papers. Okay, then we try to get all the values also nicely, you know, classified, ranked as well. Can we do that? So this 0.1% means within about 15,000 papers and authors, we took about 15, okay, papers and authors, give them labels. Then you will see what's the accuracy you can get. You probably can see this accuracy. This is the accuracy on authors. This is accuracy on papers. These are accuracy on conferences. The accuracy actually is pretty high, even use very small number of training examples. Okay. If you're not convinced, here I show you the concrete example. What are the top ranked, you know, terms and top ranked conferences? Okay. You probably can see if you are in the field. Suppose you're in the field of, say, information retrieval. You look at information retrieval. Top 5 ranked conference, we got like a SIG-IR, ECIR, CIKM, WWW, Wisdom. Of course, you may argue with me. You say, actually, WWW ranked higher than CIKM. But WWW is a little more spread. It's not just on IR, it's on many other things. Okay, if you're just focusing on one part, okay, so that makes difference. If you look at the top 5 terms, you probably, I would love you can give me other top 5 choices. For example, this is automated, nobody even doing anything. You can see in IR field, get retrieval information, web search, text. These are top 5 ranked terms. Okay, so with this philosophy, we go into a little detail on this web structure to see how we really judge this one to turn out something magic. Okay. The first thing I want to discuss is the similarity measure. How can we judge who and who are really similar? Okay. For example, we may pick up Christos Falousos at CMU. We say, who is most similar to Christos? Okay. Or you may get a Kindle, the readers. Okay. You say, what product is most similar to this one? Okay. Or which movie is similar to the other movies? So those similarity becomes very interesting. The interesting thing is, even when you ask me who is most similar to Christos Falousos, even as a human, it's hard to say. It really depends on how do you judge. Okay. So we took this schema. We say, how could you judge Christos as a researcher, as an author, is most similar to somebody else? Okay. So you can see, based on this schema, what you got is we have paper, venue, and term. It really depends on if you just say author linked with paper. You just say this, author linked with paper. Actually, what you got is co-authors, because co-author gets strongest types in this paper ID. Okay, right? So if you just using MetaPath to say author, paper, author, what you got is something like I want to find from the co-author point of view who is most similar to Christos, likely his most frequent popular co-authors. Okay. But unlikely you want this. You may say, I want to go a little further. For example, I want to go to venue. It simply says, I want to see from the venue-wise who is most similar to Christos. This does make sense. Let's look at this. Okay. We took Christos Falousos as example. We say author, paper, author. This MetaPath, you got similarity based on our measure. You get Spiros Papadimitriou, Jimen Sen, like including Yuri Leskovic. Those are mostly his or current PhD students or very, very tight co-authors, collaborators. So these are the one relationship you can find. Here, if you go a little further, you say, now I'm not going to look at MetaPath author, paper, author. I'm going to look at the author, paper, venue, going back to the author. It simply says, I actually take venue as a very important part to glue them together. So what you can see, actually, Christos Falousos, the most similar one is myself and Rakesh Agarwal, Janpei Agarwal. So that immediately turns out to be very interesting, the co-author. Why? Because we actually publish in the past and the current many papers in both database forums and data mining forums. That makes us really, like a glue together by venues. Okay. So if you look at terms, I'm not the most similar ones because I even publish in the same venue, but we are on different topics. So we do not share that much common terms. So you can see that that's very interesting to look at this MetaPath. Then we tried even on Flickr. Okay. You took a picture, like take this picture as a query. Say, this is a lotus flower. We took this one and say, which picture in Flickr is most similar to this one? Okay. It's sensitive to the MetaPath. If you think the Flickr just rely on tags, you say, I want to get like image tag image. Okay, just share common tags. These are, this is top one is most similar to itself. Okay. These are the similar ones. You probably will disagree with me because those are the birds. You see, these ducks or birds, definitely not similar to the flowers. How could that be? Just some people put the similar tags, okay? Some kind of tags, okay? I do not know. But you can look at this. This one actually not only goes to tag, but also goes to group. Simply says, they're not only similar on the tag, but also on the groups. Okay, what you'll get, you can see these top 5 actually really most similar to this lotus flower because like this one has no color similarity, but these are lotus flowers, right? But then you may say, just based on the MetaPath, without thinking of a measure, whether we can get it right, actually it's not. It's very interesting to look at the measure right. We look at several known measures, then we go back and think about it. One measure actually was called personalized page rank. developed in Stanford by Jennifer Williams' group using this formula. Another one, actually SimRank, also by Jennifer Williams' group, because the SimRank, actually one is based on, is more like a random walk. The other one is based on pairwise random walk. Okay. Then we look at this to see, using this to judge, plus MetaPath, whether we can do better. Actually, we found, random walk actually favor on the highly visible objects. That means if you are famous, lots of links linked to you, automatically for similarity, even you get an unknown person, you're probably more similar to this more visible ones because there are many links towards it. So the similarity will pull these highly visible objects to you, okay, which may not be quite fair. But we use pairwise random walk. It favors more pure objects. That means if you get many different kinds of links, somehow you will be distracted somewhere. But if you have very narrow links, sometimes you are more beneficial. Okay. But we look at the PathSim, we work out our own measure, which actually is this. You probably see from X to Y. Okay. You look at how many passes based on the MetaPath, how many real paths links link to this one versus the average of the linking to itself, to X and Y itself, okay, based on this ratio. This similarity, I give you an example, you probably will be convinced why this one is better, okay. We still look at the publications. Suppose Mike published 2 papers in Sigma, 1 paper in VRDB and 0 paper in KDD or ICD. You can make this to any venue, okay. We just assume these venues are not really linked. Of course, in the long run, you look at more, you will get a linked one. Now you look at this, Jim, Mary, Bob, Ann. You look at this, you say, who is most similar to Mike? Okay. Some people may say, oh, Jim may be similar because the ratio may be a little closer. But actually, Jim got 50 papers in Sigma and 20 papers in VRDB. You only get 2 and 1. There's no comparison, right? It's more like you get a big guru versus the first year PhD student. It's not really similar. Okay? So if you look at PageRank, personalized PageRank, SimRank, random walk, and pairwise random walk, you will see they get a very different results. You just look at this table, you can calculate it. What you got is some people vote for Jim. Okay? You can see there are quite a few people vote for Jim. Okay? And some people vote for Mary. Some people vote for Bob. Okay. Which one do you believe? Look at Jim. Okay. Mike and Jim actually look at these numbers, there are dramatic differences. Okay. So based on this, if you use this, ours, called PathSim, we say this similarity is pretty low. Okay. Actually, it's even worse than Mary. The most similar one actually is Bob. The Mary actually is, this is 2, this is 0, this is 1. It's a little similar, it's not that similar. Okay, you take the count into consideration. That means you look at the network, not only look at the structures, but also look at the numerical ones. And with this one, you go down to the real data sets to look at subtlety. For example, we intentionally put one, for example, DASFA, which is a conference, is a local regional conference in Asia on database systems, applications. Okay. Then we try to check, this one is on personalized PageRank, this one is on PathSim. So you probably can see, the interesting thing is personalized PageRank put most visible conferences like ICDE, VRDB, Sigma, those conferences, most similar to DASFA. You go to the real field, they will argue with you, say, this one is not really quality to Sigma. There's no way you can really say they are similar. Okay. Actually, the PathSim give you very interesting one is, this is like a second-tier Asia conference in the field. This one is second-tier European conference in the field. Nowadays, actually, you probably can see those people who cannot get a paper into the very top conferences, they don't care. They can send paper from Europe to Asia, from Asia to Europe. Okay. So they really link together in that way. So you can see those similar ones like DEXA, WIME, AP Web, it's really like second tier field conference, they are most similar. Okay. That means you look at not only the link, but also the count, all things considered. Okay. But we even tried, like for example, the Sigma conference, use SimRank, you get a more pure one, which actually many conferences are unknown. But if you use PathSim, you get a very top conferences in the field. That's a real similarity. We tried people, because very interestingly, we took one person we know where, who's An Haiduan, now is in Wisconsin. He was a young faculty actually in UIUC in my group, okay, as a young assistant professor. But he was doing quite well, but he was grabbed by Wisconsin, and he joined Wisconsin, okay. We want to check him, say who's most similar to him, okay. So the interesting one is if you use personalized PageRank, okay. The most similar one is a very big name one in the field, like Philip Yu, Jiawei Han, Hector Garcia Molina. Those are the big name ones, published many papers, but these are the young ones. An Hai is a young researcher, okay. But if you use PathSim, your SimRank, actually you get several people who are more pure, but it's much less known, okay. You will find they are not really similar at all. But if you use PathSim, you really get the one, probably the most similar one, Jignesh Patel. The interesting story was, no, these two are most similar. Why? Okay. If you look at the personal-wise, you probably can explain. Both are young researchers in the database field. More interestingly is both, he got a UIUC assistant professor, he got a University of Michigan assistant professor. But later, both were grabbed by Wisconsin group, joined Wisconsin. Okay. So you probably can see, even from the history, socially, they are very similar probably. But actually, we look at the publication record, these are most similar groups. So that means they are not that visible, but they are really similar. Okay, so that's very interesting. With this similarity we sorted out, we want to explore the interesting thing is what's the power we can get. Okay, the power we can get. I'm first introduce you is PathPredict. Okay, the interesting one is how can you predict something may happen in the future. Okay. The motivation was this. So I actually took the Christos Valousos, most similar to who? Okay, that was in Barcelona conference in ECML PKDD. He was sitting in the audience. He raised hands. He said, "Your PathSim looks very magic. I raised one question. Can you do it?" And I say, "What question you raised?" He said, "Can you predict what papers I'm going to write next year?" Okay. Which, of course, it's very hard to predict. I have to confess, I say, I even do not know what paper I'm going to write next year. How can I predict you? Okay. But I bring back the question to my student, Icho. She actually thought about it. She said, it may not be that hard. And the reason is, it's not a concrete paper title, but on the issues you're going to work. Okay. Those may not be very, very hard. Actually, many people may even predict what he is going to work. Okay. So she says, actually more difficult, more challenging one says, whom Christos Valousos going to collaborate if this guy has never been collaborating before with Christos? That becomes more challenging, right? Which is definitely more challenging because you even do not know what student you have to get, how could you predict? But for known authors, there's a possibility you can predict because there are already 500,000 authors in the database. Okay, who is ranked on the top? So to predict this, you need a heterogeneous network and the similarity as well. Okay, so you look at most people doing the link prediction is predicted on just the potential friends you're going to link. Okay, that's basically the network structure you want to predict. Here you do prediction. Is on heterogeneous relationships, like you're going to write this paper. Okay, you and paper are different types of things. Okay, even you say you are going to collaborate with via some papers or some conference venues or some topics. It's still heterogeneous links. We call these as relationship prediction. Okay, with relationship prediction, the first interesting thing is you look at schema. Okay, this paper. You cite this paper, you have the contains this topic, you have these 4 objects. author, paper, venue, and topic. Okay. With this one, there are many potential meta paths. If you think about author, paper, author, you are going to co-author with this guy, like Christopher Fellows is going to co-author with a new guy. Okay. This is APA relationship you are going to predict. Okay. And what other paths we're going to use? We may use many other paths. For example, we may use author wrote this paper. This paper cite, this means cite. Okay. Cite the other paper, the paper was written by the other author. Whether you are going to co-author with this guy, if you cite this paper. Okay. So we look at potential meta paths up to length 4. Okay. So you can see these are all the potential meta paths for this simple schema. Okay. The interesting thing is based on known data sets. You already know last so many years publication. Based on these known data sets, can you predict which meta path is more critical to determine the co-author relationship? Okay. So we do this using the regression analysis, using the p-score test. We immediately can see actually this similarity measure plus the meta path can easily disclose which paths are most critical. Okay. For example, you look at the p-value. Everybody knows if the p-value is very big, it's no value. Okay. It's very small, it's more valuable. You probably see those are 4-star relationships. These are no star. I can first explain no star means what. You can see if this author written this paper, wrote this paper, cite this paper cite the other paper, this paper got author. Okay. Suppose you cite somebody's paper, this guy cite Einstein. Okay. Are you going to collaborate with Einstein in the future? It's unlikely, right? So based on this, you probably see this prediction, this citation or cited by, this long chain does not really contain much valuable prediction power. Okay. So on the other hand, sheer common venues, terms, authors, those actually are very high quality ones. That means you can use this one to do prediction. Okay. Now I'll give you some real example you probably think is very interesting. With DBLP, we took a few guys. I just show you this paper. This one probably is most convincing. I took my own previous student, Jiawei. Now he's a professor in Canada. And we took the year is 2000. We use these as a training set. We predicted 2003 to 2009. Why Jiawei is particularly interesting? Because he graduated in 2002 from me. He started in 2003. He became free agent. He want to work anyone is fine, right? He's definitely okay with anyone. So with this, he definitely will seek more collaborations. We want to see those collaborations, whether we can predict. And we predicted using our method, we predict top 5. Okay. The interesting thing is within this top 5, we checked this several years. Okay. 4 of them are really true. Okay. The only one we predicted wrong, Osman Zayan, actually was his lab mate. Okay. The interesting thing is they both graduated from me. They both now working in Canada in a neighbor university. They both work in the same field, but then they never, when they were in the school, they did not write papers together. Actually, for some reason, they never write paper together. Okay, so that probably have some social reason behind. But anyway, if you look at this, you probably can see is the prediction actually is reasonably high quality. Even the student try to predict me, he gave the top 10 ones, there are only 2 or 3 actually true, but all the others, even not true, is a strong recommendation. I should work with those guys. For example, the Hans-Peter Greger is number 1, I did work with him. Christopher Fellows is number 2 recommendation, I never worked with him in DBLP, but doesn't mean I never worked with him because we co-edited a book, but the book is not in DBLP, so it doesn't count. Okay. But anyway, you probably can see it does work. Not only you can predict things should working together later somewhere, but we can predict even when it should work together. Okay. So this predict when becomes more challenging. And you probably can see that's a similar philosophy is using metapaths, but when is you trade to the future time is this become the period. You try to use a logistic regression. generalized linear model, not just a logistic regression, you use generalized linear model, you actually can predict the time on the probability part. Okay, just to show you, we identified these several important metapaths. Using this metapath and data, we predicted Philip Yu, when he's going to cite this new author. Okay. So we predict the years. The interesting thing is among these top predictions, there are about, 2 are not very good, but the others actually predicted when you're going to cite a new author, actually predicted reasonably high accuracy. Okay. Then immediately people may say, you've got so many metapaths. Of course, for some reason you have training, you probably can select a good metapath. What about you do clustering? Okay. You do clustering, can you get metapaths? You do not even have a standard. Okay. But what interesting thing is the user can give you certain influence. You think about this. Just give you an example. Suppose you look at these are the institutions. These are the conferences. These are the authors. See, these authors publish in different conferences. They are in different institutions. When you try to do cluster, there are many ways you do cluster. One is you focus more on the conference. Another is focus more on the institution. The third one could be some kind of weighted combination of both. Okay. But how could you know what I mean? That means you even do not, you cannot put in my mind to say what exactly I'm thinking to do clustering. But what I can do is I may ask you to give a bunch of seeds. Say who and who is more like a must link or cannot link, this semi-supervised idea. Okay. That means if you give me certain seeds, I immediately can know which metapaths I use, probably give you better ones, more coherent with the seed. So you probably can look at this. If I give you a seed, say 1 is a cluster, 5 is a cluster, I don't have to give you all of them. I just give you this 2. So you probably can get me like this cluster, like this. And if you give me something like everyone is an individual cluster, I probably were like this 1, 2, 5, 6 are individual clusters. I may give you a different metapath. I give you a metapath which is weighted combination of the both. Okay. So you probably can see the learning thing is can use, seed to do the guidance. Okay. And we work out this. I probably give you, skip up exactly the statistics modeling on this. I probably show you some interesting example you can see. This is Yelp. You probably know the Yelp actually is rating and ranking on different things, services. For example, there are services on restaurants. There are services on shopping. Okay. Then you give different seeds on those clusters. You don't have to give all of them. So you probably can see we actually you can learn the metapaths based on selected by users a few seeds. The learning actually finally you both look at the accuracy and NMI. Actually, you probably can see it got pretty high compared to many other methods. Okay, you can see this is extremely high with others. Another interesting thing is we tried both on the restaurants and the shopping. We found actually they really have different weights, dramatically different weights on these 2 competitive metapaths. Okay, one is business. This is their business review and user and terms. You look at this is business review, user review, business. This is business review and term. One is critical on the user. One is critical on the term. And we found the interesting thing is for shopping, you look at this on the user, and restaurant on the user. The distinguishing is restaurant is much weaker than the shopping. What you can see from this one is actually people go to many different kinds of restaurants. That means you may want to try Thai food, Japanese food, Italian food, and French food. Okay, but once you do shopping, the user a little for those shopping, different shops, they are a little more focused. That means you're not going to shop every store, okay, every style of store. Okay, you shop more, more focused than restaurants. Restaurant, you actually look at the cluster. You have Japanese, Chinese, and different things. You probably try more, varieties. So it's very interesting to look at this from the Yelp data. Then the final question I'm going to raise actually is, you got network we call heterogeneous network. The previous one I gave you are all nicely constructed networks. But in real life, the network is not nicely constructed. Just give you an example, okay? For example, news. If you want to do nice ranking and clustering on news data or Twitter data, they are not nicely typed. Okay? Even you imaginarily, you can say, those are the news, like events, Obama, like Putin or somebody, and these are something. You know it, but the computer doesn't. Okay? You need somehow to extract them, type them. Okay? So method, you can see there are many methods need to be done before you can construct quality heterogeneous network. So you can see these are the typical methods, NLP machine learning. You get typing, information extraction, entity resolution. There are many things has been done. I'm not going to address this. Another thing is using data mining, you can do a lot of raw and hidden structure discovery. Okay? And you can do the truth analysis or web structure discovery, and putting them together, progressively refine them. You probably using typed network to do better typing. Okay? Clustering and classification to do better typing. Just give you one example. We try this in DBLP. We try to discover who are whose advisors in which years. Okay. The interesting thing is you constructed this heterogeneous network graph, okay, by putting a small number of constraints. For example, the constraint says the advisor will have more papers published and longer publication history at the time of advising than advisee. You probably will agree. If you publish much more paper than your advisor, when you're looking for advisor, you probably find another one. Okay, so that's one. Another one is if advisee become advisor, you will not become advisee again. That's probably also true, because when you become professor, you don't want underneath to somebody to start your year one PhD study, right? So using this, actually using the year, publications and collaborations, all these, you can construct a very nice graph with constraints. I just give you a few examples. You probably can see this really have the power. It's just based on even without citation. Okay, we took David Blake. Okay, probably everybody knows him. Anyway, we just say who are David Blake's advisors. Okay. We found using this graph, you can easily get two. One is Michael Jordan. One is John Lafferty. Okay, actually the real truth is. David Blake got a PhD from Michael Jordan in 2004, but our prediction actually is Michael Jordan, the time is 01 to 03. That's based on the publications, okay? And the other one is 05, 06, based on this short time, actually unlikely to do PhD under John Lafferty, actually is a postdoc. So even using my own student, the student found two, one's Chang, one's me, actually even a year and publications is almost exactly identical as a prediction. Okay. We took a Serge Brand from Stanford. Okay. Yeah, so the interesting thing is that's the only one we made a mistake, even for the big guy, is we predict Rajiv Modwani. Okay. It's 1970 to 98, with such a short time, unlikely to finish a PhD, but we say Rajiv was Serge Brand's advisor. Okay. And I put this one, actually this year in UCLA, give a talk. And after the talk, Carlos Aniolo said, you made a mistake. I said, why? He said, actually, Serge Brand's real advisor was Hector Garcia-Molina. But Hector was department head, was so busy. He got no time to take care of him. So actually, Rajiv got the most publications. He got no publication with Hector, but he got quite a few with Rajiv. That's why our data sets can only do this prediction. Okay. Another interesting thing is how to get this network structured. Is you go to the web. Most people thinking the web, you try to find structure is almost impossible, but because the people so can create a web page so freely, can link so freely. We tried because we think actually the reader, for example, you get one professor. you try to find all the professors in, say, UIC computer science department, whether you can do it automatically in this easy way. We actually found if you using, we call growing parallel structures, just because they are in the similar space, you just look at structure differences based on HTML structures or XML structures, you can do very good result. You can get a very good result. The interesting thing here, you can see using our method here, the last one. Actually, there are many other things we can get 100% recall, 100% precision. The only thing we have to regret is computer science faculty, because there are so many hackers among computer science faculty. They put their homepage in LinkedIn or in some kind of Facebook. So just not in their regular, assigned space. That's why with those people, we actually could not find them. Otherwise, it's still very close to 100% recall and precision. Another interesting thing is you structure this, you may get lots in the real web or real data sets, there are lots of noise, okay? Once you get a conflict information, which one is true, okay? And using the network model, you actually can judge, not only model the positive, but also model the false negative in a nice way. Then you can get the truth sorted out and clean up automatically without training, okay? Clean up this data sets to get a high accuracy and F value, F measure, okay? So this actually was done with Microsoft Research with very large data sets, like a book author, movie data. It's from almost like hundreds, thousands of claims without any single training, labor data, and get a very high accuracy. So finally, I will conclude saying the structure actually is very important. Structure in a multiple typed network give you very rich knowledge, you can explore it. Okay? That's all. I just give you a simple example using those DBLP, Flickr, IMDb data. But there are lots of real data sets we can do this, like PubMed, like Wikipedia, Google News. Of course, lots of things not quite explored. But we think there are lots of grand challenges in this field we can explore. So what I probably can introduce you is, if you're interested, you can go to my webpage, download many papers. But there's a book coming out this month. Okay, it's an ebook. It's not quite published yet because we are doing the final editing with the editors. It will be published this year by Morgan Claypool publisher. It will be an electronic book. In Stanford, I think once it's published, you can free download it for sure. Okay, so you may look at this. It's very interesting. And I finished my talk. This is the UIUC campus. It's a little more spacious comparing to Stanford. so there are lots of land. This I just took a small corner. So that's a difference, but definitely Stanford campus is very impressive. Thank you.